Good afternoon, everyone. My name is Jack Wong from the Chinese University of Hong Kong. First of all, I would like to thank the organizing committee for the invitation to join this meaningful health forum. It's my great pleasure and honor to have this opportunity to share our recent work. According to the latest WHO survey, cardiovascular diseases, CVDs, are the leading cause of death globally, taking an estimated 17.9 million lives each year. These cardiovascular diseases affect the heart and blood vessels and include ischemic heart disease and stroke, shown here in this graph as the first and second greatest contributor of mortality globally, respectively. Among the various risk factors associated with cardiovascular disease, metabolic syndrome is a major one. Metabolic syndrome is characterized by high blood glucose levels, low levels of high-density lipoprotein, regarded as the good cholesterol, high levels of plasma triglyceride, and high blood pressure. One of the greatest contributors of cardiovascular risk is diabetes. As we can see with this graph, the risk factor of cardiovascular disease is almost twofold for patients with diabetes, especially as one ages. Complications that can arise from diabetics include diabetic retinopathy, stroke, diabetic nephropathy, diabetic vasculopathy, etc. The underlying mechanism for the development of cardiovascular disease is a metabolic one. Specifically, it's the development of plaque in our blood vessels. This hardening within our blood vessels is called atherosclerosis. While some plaque buildup is normal over the course of our lives, excessive buildup of plaques lead to life-threatening outcomes. These include myocardial infarctions, stroke, peripheral arterial disease, and chronic kidney disease. As the development of plaque occurs over a long-term scale, the diagnosis and treatment of complicated plaque formation is very important. Atherosclerosis begins with endothelial injury. The endothelium is a thin wall of cells that line the inner walls of our blood vessels. These cells form a barrier between the circulating blood and the outer tissue layer, and control the flow of substances and fluid in a given tissue in our body. The likelihood of occurrence of CVD increases in the presence of multiple risk factors, which may be modifiable or unmodifiable. The non-modifiable risk factors are age, gender, and family history. And the modifiable risk factors are dyslipidemia, hypertension, eating habits, smoking, diabetes mellitus, obesity, and sedentary lifestyle. Atherosclerosis rarely forms in the areas of undisturbed or laminar flow in blood vessels. Instead, areas exposed to high turbulent flow, especially in areas of branching or curved blood vessel, will have higher areas of disturbed blood flow and thus more plaque formation. Upon closer inspection of the endothelium itself, the normal condition of laminar flow results in positive effectors of endothelial cells, such as the production of nitric oxide, NO, which is involved in a variety of pathways, such as the prevention of monocyte adhesion, pellet aggregation, and smooth muscle cell proliferation. In the disturbed flow state, the endothelium will be subjected to a variety of negative effectors, such as the deposition of LDL, also called the bad cholesterol, the expression of molecular adhesion cells, macrophage migration, as well as the expansion of smooth muscle cells. Endothelium-dependent relaxation of blood vessels is produced by a large number of agents, including acetylcholine, ATP, ADP, substance P, to name a few. With some agents, relaxation may be limited to certain species and/or certain blood vessels. Relaxation results from release of endothelium-derived relaxing factors, including nitric oxide, NO, prostacyclin, PGI2, and the endothelium-derived hyperpolarizing factors, EDHF. On the other hand, endothelium-dependent or endothelium-derived constricting or contracting factors appear to be responsible for endothelium-dependent contractions produced mainly by arachidonic acid and hypoxia in some of the isolated systemic vessels. EDCF appears to be some product or byproduct of cyclooxygenase activity and superoxide anions. To maintain vascular homeostasis, there should be a balance between EDRF and EDCF. However, in pathological conditions such as hypertension and diabetics, an increase in EDCF as well as a decrease in EDRF will favor vascular contraction and potentially pathophysiological changes. Then, therapeutic intervention is needed when there is an increase in EDCF and when there is a decrease in EDRF. Treatment should increase the production of EDRF and decrease the vessel resistance by making the vessel more dilated. Even during the current pandemic, CVDs is an important public health issue as well. On one hand, the presence of underlying cardiovascular comorbidities in patients with coronary disease 2019, the COVID-19, is associated with high mortality. On the other hand, COVID-19 can cause cardiovascular disorders, including myocardial injury, arrhythmias, acute coronary syndrome, and venous thromboembolism. Importantly, the prevention and appropriate treatment of CVDs could help lower the risk of COVID-19 mortality. One of the risk factors of CVD is menopause. A recent report published in Circulation found the prevalence of CVD increases with age in both women and men, but is less prevalent in women than men until midlife, as shown in this left graph. Thereafter, the gap narrows where the prevalence of CVD no longer differs between the sexes, implying a decrease of vascular protection in female after menopause. In the right graph here, we can see that the endothelial function, as measured by the brachial artery flow-mediated dilation, FMD, begins to decline during the early stages of menopause or the perimenopause, and worsens with the loss of ovarian function and prolonged estrogen deficiency, indicating that the perimenopausal window is a critical time period to intervene at first changes in CVD risk. To mitigate the likelihood of CVD, there are several risk factors that can actively be improved through lifestyle changes. The American Heart Association, AHA, has defined 7 factors that people can improve through lifestyle changes, including smoking status, physical activity, weight, body blood glucose, cholesterol, blood pressure, as well as diet. In a systematic analysis on the global burden of dietary risk, it was determined that dietary risk factors contribute to around 22% of death and 15% of disability-adjusted life years globally. Furthermore, other studies have found that improving dietary quality could greatly reduce premature deaths. Changes to what we can eat can greatly affect the overall physiological well-being of the general population. Specifically, deterioration of dietary quality led to the increase in major chronic diseases, with cardiovascular diseases as the largest proportion of diet-related death and disability. Diet indeed has a profound and immediate impact upon the bioactivity of lactic oxide generated by the endothelium. Chronic nutritional interventions by modulating endothelial lactic oxide synthase (ELOX) can dramatically affect vascular homeostasis. NO activates soluble granulate cyclase and increase intracellular cyclic GMP, relaxing the vascular smooth muscle cells to improve vascular compliance and to reduce vascular resistance. Moreover, NO inhibits pellet adhesion and aggregation, suppresses leukocyte adhesion and vascular inflammation, and limits the proliferation of the underlying vascular smooth muscle cells. The main functions of the lactic oxide is illustrated here, including inhibiting pellet aggregation or adhesion, blocking monocyte invasion, inhibiting vascular smooth muscle cell proliferation or migration, blocking matrix formation, inhibiting endothelial cell apoptosis, causing vascular smooth muscle cell relaxation, inducing re-endothelialization, as well as inducing vascular smooth muscle cell apoptosis. There are three main diet components, namely lipids, protein, and carbohydrates. Diet composition is one way for us to actively alter and improve the function of the lactic oxide synthase pathway and thus promote cardiovascular health. Of the various different dietary components that could significantly improve cardiovascular health, dietary supplements such as soy protein and phytoestrogen could greatly promote cardiovascular health. Among different patterns of diet low in legumes, which indicates mean daily consumption of legumes less than 60 grams, contributes particularly to CVDs, indicating that diet, especially the consumption of legumes, is a useful and possible source for CVDs intervention. The nutrient compositions between legumes themselves are not the same, as we can see in the table here. Beans have long been recognized for their protein contents. However, soybeans are unique among legumes in that they not only have high levels of protein composition, but also a concentrated source of isoflavones. In the Asian literature of traditional Chinese medicine, TCM, soybean has several functions like relieving internal heat or fever, invigorating the circulation of blood, and relieving pain. In recent studies of soybean-derived polypeptides are found to have many effects, including anti-cancer, anti-diabetic, anti-oxidative, anti-inflammatory, anti-hypertensive, immune-stimulating, and triglyceride-lowering effects. You can see in this graph that soy products exist in different forms in our daily life. The protein and isoflavones content of some soy foods are shown in this table. In general, soybeans and soy products contain around 3 mg isoflavones per gram of protein. Soy isoflavones, also called soy phytoestrogens, have antioxidant and anti-inflammatory effects. The main soybean isoflavones are genistein, daisine, and glycine. As you can see from the structure below, the compounds of isoflavones are very similar in structure and function to 7-estradiol and can bind to estrogen receptors. This table on the left shows individual isoflavone contents in a variety of soybean products, and on the right, it shows the chemical structure of the soy isoflavones. The mechanism for isoflavone-induced vasodilatation, as with estrogen, is assumed to be mainly through stimulation of anal production in endothelial cells via both genomic and non-genomic estrogen receptor-mediated activation of ELOS. It is possible that isoflavone can also act directly to increase the ELOS activity, not through the estrogen receptor. Therefore, in this study, our objective is to investigate whether soy isoflavones would benefit vascular function in overoptimized OVX mice and the underlying mechanisms that regulate these benefits. In our study, we established a post-menopausal model by conducting a bilateral ovarectomy to female C57 black 6 mice. We divided the mice into 4 groups. The first group is control, while the remaining groups receive ovarectomized surgery. The photos on the right are snapshots of the surgery. You can see that the ovary was removed after the surgery. After 8 weeks, we added soy isoflavones to daily diet of group 3 and inserted estradiol pellets into the subcutaneous tissue of mice in group 4. OVX mice in group 2 and 4 kept having normal trial diet, and the mice were raised for 8 additional weeks before collection of tissues and functional analysis. As you may recall, menopause is a risk factor of metabolic syndrome, and metabolic syndrome is a major risk of CVD. We observed the phenotypic changes in OVX mice. You can see clearly that 8 weeks after surgery, as expected, the OVX mouse look fatter than mice in other groups, while mouse fed with soy isoflavones were slimmer. The OVX procedure consistently caused estrogen depletion in female mice, resulted in a lighter uterus of OVX mouse compared with that of the control counterparts. The uterus in mice receiving estradiol pellets are significantly heavier than that in mice from other groups. These data indicates that soy isoflavones can counteract the weight gain observed in OVX mice. Besides obesity, blood glucose is another key parameter in the diagnosis of metabolic syndrome. We examined the overall blood glucose level of the OVX mice. We found in the oral glucose tolerance test, OGTT, that the blood glucose increased significantly in OVX mice 15 minutes after intake of glucose and could not return back to the original levels. The impaired glucose tolerance is represented as an increase in the area under curve in the right graph. Mice taking soy isoflavones exhibited improved glucose tolerance, which mirrored the control group. As diabetics doubles the risk of CVD, our results suggest that the use of soy isoflavones can lower the CVD risk in OVX mice by improving their overall glucose tolerance. Since OVX mice develop obesity, we then weighed the adipose tissue. White adipose tissue stores excess energy as triglycerides, while brown adipose tissue, BAT, dissipates stored energy as heat. As shown in the left graph here, soy isoflavones intake reduced the weight of white adipose tissue, including the subcutaneous fat, the perigonadal fat, as well as the perirenal fat in overrectomized mice. Since white adipose tissue is considered as a major source of obesity-related inflammation, we analyzed the cytokine monocyte chemoattractant protein 1, also named as CCL2, whose expression is induced by inflammatory stimulus. The expression level of CCL2 in white adipose tissue increased significantly in OVX mice. The levels of CCL2 were suppressed in the mice which took soy isoflavones, implying that soy isoflavones not only decrease the weight of the white adipose tissue, but also the expression of inflammatory markers within these tissues. Next, we assess the endothelial function by using the wire myography method. We observed that the acetylcholine-induced endothelium-dependent relaxations were impaired in the aortas of the overactomized mice compared to the control mice. Importantly, isoflavone-treated overactomized mice significantly improved the endothelial function. On the other hand, on the left graph of it shows the representative traces of the 4 different groups. On the other hand, the sodium nitroprusside, the SMP-induced endothelium-independent relaxations were the same among the 4 different groups, suggesting that the beneficial effect of soy isoflavones on vascular relaxation is endothelial-mediated. Reactive oxygen species, or WOS, are reactive intermediates of molecular oxygen that act as important second messengers within the cells. However, an imbalance between the generation of reactive oxygen species and antioxidant defense system represents the primary cause of endothelial dysfunction, leading to vascular damage in both metabolic and atherosclerotic diseases. Here, we stained aorta with dihydroephedrine DHE and monitored the DHE oxidation-derived fluorescence by confocal microscopy. The red fluorescent intensity is correlated with ROX production. As shown in the left micrograph, the red fluorescence was stronger in OVX aorta compared with control groups, while the soy isoflavones group generated much less fluorescence. The histogram on the right is the summary of 3 repeated experiments, which in all indicates that soy isoflavones decrease the ROS production in overactomized mice aorta. In 2019, a PNAS paper showed that epigenetically upregulated FKBP5 is associated with inflammation and cardiovascular risk. FKBP5, or called the FK506 binding protein 5, itself encodes a protein implicated in stress physiology. The authors proposed that FKBP5 might be a possible biomarker or therapeutic target for stress-related disease such as CVDs. First, we use FKBP5 as a marker of CVD risk and determined its expression level in OVX mice aortas and adipose tissues. Consistent with the findings in the paper previously mentioned, we observed increased FKBP5 level in both types of tissue in OVX mice. In the aorta and the perigonadal fat, soy isoflavones significantly suppressed the upregulation of FKBP5. In the subcutaneous fat, although the difference is not statistically significant, we can still observe a decrease of mean expression level in soy isoflavones group compared with the OVX group. To elucidate the role of FKBP5 in vascular function, particularly in the aorta, we treated SAFEIT2, an antagonist of FKBP5 to the OVX mice. We observed that the impaired acetylcholine-induced endothelium-dependent relaxations in the OVX mice were rescued by the SAFEIT2 treatment, an effect similar to the isoflavone treatment. Similarly, we find that SAFEIT2, the FKBP5 antagonist, also helped improve glucose tolerance in OVX mice. Then we wanted to determine how soy isoflavones regulates FKBP5. From the literature, we found that a microRNA 511, could bind to FKBP5 messenger RNA, suggesting that microRNA 511 can bind and target the FKBP5 messenger RNAs to induce translational inhibition or lead to messenger RNA cleavage. With this idea in mind, we detected microRNA 511 levels in adipose tissues. An increase of microRNA 511 was observed in both subcutaneous fat and peritoneal fat in OVX mice receiving either soy isoflavones or the estradiol pellet. This again suggested an inverse correlation with the FKBP5 level in white adipose tissue. Using an ELISA assay, we also determined that corticosteroid level was significantly increased in the OVX mice serum, while the treatment of soy isoflavones could reduce the increase in corticosteroid levels. Corticosterone is a steroid hormone of the corticosteroid type produced in the cortex of the adrenal glands. Its level is regarded as a reflection of stress. Besides the mouse model, we also aim to mimic the stress condition of OVX mice in vitro. Due to the complexity of the cellular composition in blood vessels, we simplified our in vitro model by treating mouse brain microvascular endothelial cells with 1 micromolar dexamethasones for 24 hours to mimic stress on endothelial cells. Dexamethasones, DEX, is an artificial glucocorticoid with a potency approximately 25 times greater than that of the naturally occurring corticosteroid. We treated the cells with 100 nanomolar SAFET2 as well as 100 nanogram per ml soy isoflavones to determine changes in ROS level after dexamethasone treatment. We observed that the ROS production was elevated in the dexamethasone treated group, which could be reduced by either soy isoflavones or the SAFET2. Meanwhile, the real-time QP cell results showed that FKBP5 was increased in the dexamethasone-treated endothelial cells, and the addition of soy isoflavones or SAFET2 downregulated FKBP5 levels. As described earlier in the presentation, nitric oxide is synthesized by the endothelial isoform of nitric oxide synthase, ELOX, in vascular endothelial cells, and the effects on ELOX abundance are primarily mediated at the level of gene transcription. First, we detected ELOX messenger RNA level in endothelial cell as well, which showed a downregulation of ELOX transcription levels caused by dexamethasone treatment. In the endothelial cells treated with either soy isoflavones or the SAFET2, we observed an increase in the ELOX level, indicating that an increase in nitric oxide production and improved endothelial function. First, in summary, we have found that in the context of a mouse model of postmenopausal women, the dietary inclusion of soy isoflavones protects against cardiovascular disease, specifically by improving endothelial function through the lowering of ROS and FKBP5 in endothelial cells. Moreover, we observed that the decreased expression of FKBP5, a stress activator in endothelial cells, were proportional to the increase of a microRNA 511, when those cells were treated with soy isoflavones. These results suggest a role of soy proteins and isoflavones in improving the nitric oxide synthase function in the endothelium and as a therapeutic strategy to promote cardiovascular health. Last, thank you for your attention, and this is the end of my presentation. Questions are welcome. Thank you.